I have a couple of slides, like just recapping what we saw yesterday. So today what I wanted to go over was try to introduce the various approximations that are in density functional theory, the various basis sets that people use, the various codes, what basis sets they use, what the pros and cons of these basis sets are. I'll also go over like some aspects of the numerical methods that people either use or have developed like very recently, and also touch upon how you can reduce the computational complexity of density functional theory calculations in certain special cases, like where linear scaling methods have been developed. And then finally, I'll just give my personal opinion on what impedes or what are the rate limiting steps like for DFT calculations to be pushed to Exascale. So starting off, this is just a recap of what we saw yesterday. So the starting point of like all electronic structure calculations is if you're interested in ground state properties, it would be the time independent Schrodinger equation, which is a very large eigenvalue problem. And H is the Hamiltonian there, which includes the kinetic energy of electrons, the kinetic energy of nuclei, the electron-nuclear interactions, the electron-electron interactions, and the nuclear-nuclear interactions. The wave function is a position of the wave function depends on the positions and spins of like all the n electrons as well as the m nuclei. We typically work under the Born-Oppenheimer approximation, but I should also emphasize that this approximation has its limitations, and in many cases it's a good approximation, but there are well-known examples where this approximation fails. It's a computationally complex, the computational complexity is huge, so you can't like solve for the full wave function when you have n anywhere beyond a few tens of electrons. So that's where I think the statement that Hohenberg, Cohen, and Sham showed and then developed a strategy in 1964-65 was a game changer. And what they said was that the ground state properties is a functional of the electron density, to be precise, ground state electron density, as Richard was mentioning yesterday. And so it's, as I was showing yesterday, to see this, we start from a state vector psi. The energy is given by psi h psi. That's always greater than or equal to the ground state energy E naught. So you can evaluate the ground state energy by minimizing over all wave vectors psi of psi h psi. Here T is the kinetic energy operator. This is the electron-electron interaction. This is the electron-nuclear interaction. And then because we are in the Born-Oppenheimer approximation, this is treated classically. It doesn't depend on the wave functions. And a consequence of, if you look at this external potential, this is dependent at a time only on the position of a single electron. So there's a single electron operator. And that's why this reduces to being integral of the electron density times the external potential. But whereas the first two terms over there still depend explicitly on the wave function psi. So, but as we saw yesterday, we can split this minimization over all admissible wave function psi into two minimizations. One is a minimization over all the electron density, and another a minimization over all wave function psi giving a particular electron density rho. Now, if we look at the eventual output of what is what comes out of like this particular minimization process, that will be a functional of rho. Because you pick a rho, you do this minimization process, you get an energy out of it, right? Or a number out of it. Now you do that across all the function space of rho, and then you get that functional f of rho. And this is what is the Hohenberg-Cohen functional. We know that this is universal because, as you can see, the minimization inside of this round bracket does not have any information about what system we are talking about. All information about the system is in this external potential, which is the nuclear potential that's provided by the atoms in your condensed matter system. And another clever thing that Cohen and Sham did was that take this particular Hohenberg-Cohen functional and they split it in the following way. This is the kinetic energy of non-interacting electrons. This is the Hartree energy, or the classical electrostatic interaction energy. And then everything else, which is the interactions between the electrons coming from the kinetic energy, as well as all the effects of like this 2-electron operator that cannot be described by this classical electrostatic potential are all lumped into this exchange correlation functional. So we've not done anything, or rather, at this particular point, there's nothing interesting excepting the fact that the unknown, which is f of rho, now gets translated to the unknown, which is exe of rho. But one of the important aspects is that in the split, you have a kinetic energy of non-interacting electrons. And so what Kohn and Sham were trying to do in this theory was they took an interacting system, which is governed by the time-independent Schrodinger equation, and they said, can we replace the system with a non-interacting system where the electrons don't see each other directly, but the electrons see the mean field that is provided by all the interactions as such. And they were able to show that, yes, you can do that. In the original approach, like, where Kohn and Sham proposed, the proof was a little different. They showed that you can do that. And there is a one-to-one map between the external potential, the ground state, many electron wave function, and the electron density. So which means that all the properties can hence be described just solely by the ground state electron density, right? So now, in some sense, because we have a non-interacting picture over here, if we take the variation of this particular ground state energy with respect to the electron density, what that gives us is this Kohn-Sham eigenvalue problem. And here, the Kohn-Sham Hamiltonian comprises of a Laplace operator and this effective field, which is the mean field that every electron sees in the system. And psi I over here is a single electron wave function, and epsilon I is the corresponding energy level. Now, this effective potential itself, like, it depends on the electron density and the positions of the nuclei, which are collected in this vector R. And this effective potential has three terms, which is essentially nothing but, if you go back here, it's a functional derivative of this term, which gives you the external potential. It's a functional derivative of this term, which gives you the Hartree potential. And it's a functional derivative of this term, which gives you the exchange correlation potential. Now, if you look at it, the effective potential depends on the electron density, but the electron density itself is computed from the solutions of this eigenvalue problem. So here I'm assuming that each energy level is filled by 2 electrons because spin up and spin down channels. But if you have any spin orbit coupling or any other terms in the Hamiltonian, the spin up and spin down electrons needs to be treated separately, and then they have their own Kohn-Sham Hamiltonians that you need to solve for. But to keep the discussion simple, I'm just looking at a spin independent Hamiltonian formalism. Okay, so now one of the key aspects here is that the Kohn-Sham Hamiltonian depends on the electron density, which is also part of the solution. So you have to solve this problem in a self-consistent manner. So there's a fixed point iteration that goes on over here. Now, once you solve this self-consistently, then you can compute your kinetic energy of non-interacting electrons. That's given in terms of this single electron Kohn-Sham orbitals. That will be your kinetic energy of the electrons. And then the total ground state energy is the kinetic energy plus the sum of all the other remaining terms. Okay? And once you have the ground state energy, that's for a fixed position of atoms. Now you might want to do structural relaxation. So which is nothing but then you're going and taking the derivative of this ground state energy with respect to the positions of the atoms. And you can actually show that in a continuous sense, it is nothing but classical electrostatic interactions. You compute your potential corresponding to both the electrons and the nuclei, take the gradient of the potential and multiply by the nuclear charge. That gives you the force on a particular atom. But of course, that is in a continuous sense. Once you are in a discrete basis set, you have to take into account considerations as to, if you want to be variational, because any time we discretize this formulation and you try to use numerics, we want to ensure that the forces that we compute are variationally consistent. So you may get some additional contributions because of the numerical discretizations one uses, but at least in a continuous sense, it is nothing but gradient of the electrostatic potential times the nuclear charge. So you have your forces, you can also compute your stresses, you can equilibrate, and then like you can compute a whole host of properties that can be computed from ground state calculations. But if we look at like this whole formulation and what are the computationally most intensive steps, one aspect is the solution of this eigenvalue problem itself, because we have to compute as many eigenstates as there are number of electrons in the system. So we're filling all the lowest lying eigenstates, so you have to compute for all the eigenvalues and corresponding eigenvectors of the spectrum of this particular Hamiltonian. So that conventionally scales as cubic scaling, because that's the diagonalization cost for any Hamiltonian that you pick. So this is still good because you have, although like cubic scaling sounds like really large, it's at least better than the exponential scaling that you have in solving the full Schrodinger equation. One thing I want to emphasize, and I'll touch upon this a little bit later, is that the solution of the eigenvalue problem is typically the dominant cost when you start getting to like larger scale calculations. But there are other formulations for this exchange correlation functional where that can become the dominant cost if you start like treating certain approximations of exchange correlation functions, which I'll introduce in a bit. Okay, so far, what I've like given over here is basically the plain vanilla description of density functional theory. And I didn't emphasize this, but this is in a non-periodic setting. Once you go to a periodic setting, so let's say that you have a lattice, a periodic lattice, then your external potential is going to be periodically repeating. You would expect that the electron density is also going to be periodic with the periodicity of the lattice. But one important aspect is that the wave functions, the single electron wave functions, need not be periodic with respect to the unit cell itself. So in fact, like using the Bloch-Floquet theorem, you can show that the eigenstates or the Kohn-Sham orbitals can be written as a Bloch factor e to the power ikx times another function, and this function will be periodic with respect to the unit cell. Okay, so and that's essentially like what I wrote down over there. I'm just writing this in 1D. It's the same thing in 3D as well, and then you apply von-Karman boundary conditions and say that this wave function becomes periodic at some very large distance, L, where like you have, if the periodic distance between two atoms over here is A, then like it maybe becomes periodic like at n lattice lengths, right? And that gives a discretization for your K space being some integer multiples of this 2 pi over L, right? And this is what introduces to, so this is what I did for 1 dimension, but you can go and do this in 3 dimensions. So I'm just making this a bit more generic. So now your single electron Kohn-Sham orbitals like have this K index, right? Now this psi nk can be written in terms of a Bloch factor times UNK over here. UNK is what is periodic with respect to the unit cell over here. And now you can substitute this particular form into your original Kohn-Sham equation. And when you take the Laplacian of this e to the power ik dot r, UNK of r, you can reduce the problem. Instead of solving for it in terms of size, you can now solve it in terms of these functions which are periodic on the unit cell, but then like your Hamiltonian changes slightly, and then the K comes into your Hamiltonian. Okay, and your electron density now also has a sum over K, and then you have like certain weights, which is essentially associated with sampling the Brillouin zone, the first Brillouin zone. So I didn't remark about like this. Fi's over here, this Fi's over here are what are the occupancy factors, which is if a particular electron occupies a particular energy state, then that occupancy factor is going to be 1. If the electron does not occupy, then it's going to be 0. But so essentially, you can think of this occupancy function as a step function, right? So it's 1 like for all the lowest lying eigenstates and suddenly drops us to 0 for the states that are not occupied. But having such a step function can be tricky in terms of getting the numerical convergence for this self-consistent field iteration, because you can have charge sloshing. So think about a simple example like a carbon atom. Like it has 6 electrons. It's 1s2, 2s2, and 2p2. But in the p orbitals, like px, py, pz are degenerate. So the 2 electrons can either occupy px, py, py, pz, or px, pz. Now, if you had a step function like this, it would say that it occupies 2 of the 3 orbitals, but which of the 2? Right? That is not clear. So what you will see in this particular self-consistent iteration is that the energy doesn't change, but your electron density keeps sloshing based on whether it's occupying x and y and z, or z and x. And then you will see that the solution doesn't converge, right? So when you have these kinds of degeneracies, it helps to smear out like this particular orbital occupancy to what is called as the Fermi-Dirac distribution, or like there are other variants of this which are more efficient, but at least the Fermi-Dirac distribution has a theoretical basis in terms of extending these electronic structure theories to finite temperature theories. So if you take the Fermi-Dirac distribution, all it's saying is that, well, you have a smearing, and then the smearing width is like roughly proportional to kb times t, and then that solves like many of the pathological issues that you see in the fixed point iteration itself. Okay, so now this is the first point of parallelism that shows up in any DFT code, right? Because you see that over here we have to compute the solutions of u and k's for many k points. And for each of the k points, this is an independent problem that you're solving. So you can take this particular problem for each of the k points and put it on different subgroups of like MPI tasks, right? I mean, you can create a subcommunicator, put this on different subcommunicators, and then get some kind of pretty much a trivial parallelism out of it, as long as the solution to this problem is the dominant cost. And that is mainly the reason you will see that many of the codes which have a limitation on scaling its basis set first ask you to scale on k points, because you will not take a hit when it comes to scaling on k points. Okay, so this is a trivial parallelism that's exploited in almost all density functional theory codes. Okay, now getting to this particular, so now I want to start talking about the approximations that come in density functional theory. So as I mentioned, we know that there exists a exchange correlation functional which is dependent on density, and as Volker pointed out, this is true only if the densities are V representable, that is, the densities are coming from some kind of external potential from the full Schrodinger equation that is generating this density. But we don't know what its functional form is, right? And this has been the holy grail of density function theory. There has been active work in this field for as long as density functional theory came into existence. And some of the earlier, most successful functionals were developed in the early 80s. And this, John Purdue calls this the Jacob ladder, right? So this is basically increasing sophistication of introducing the exchange correlation functionals. So some of the earlier ones, essentially what they said is, well, let's just do a local density approximation. So what that means is that let's take this exchange correlation functional, right, and say that the energy density, you can always write the exchange correlation functional. So if we have an EXC, which is a function of rho, we can write this as so there's no loss of generality in writing this as an integral of an energy density. And now, what some of the earliest models did was, well, let's say that the energy density at a given point, so because this is, so at a given point, let's say that the energy density only depends on the electron density at that point, right? So that is why it's called the local density approximation, right? And there's not too much of even leeway in this local density approximation. So what the earlier models did in the local density approximation was they took uniform electron gas and then did quantum Monte Carlo simulations and then fit this exchange correlation functional to basically that uniform electron gas. And remarkably, that particular local density approximation works well for a good class of systems, and at least if you're interested in structural properties. Of course, it depends on okay, what is the eventual accuracy that you want to reach? But in 1980s, I think it was a remarkable success that you were actually able to dramatically improve from the Hartree-Fock approximation the energy values that you're getting to telling something about the binding in the system and the cohesive energies and things like that. And in the 1990s, there were a group of people, including John Purdue and others, where they introduced functionals that not only depend on the electron density, but also depend on the gradient of the electron density. And that's what's called the generalized gradient approximation. And there was some theory behind this. And when they were developing these functionals, they were careful. There were some known properties that this functional has to satisfy. They took into account all those aspects. And then they did some little bit of fitting as well, depending on which functional that you're talking about over here. So that's the second rung in the ladder. And the third one is what is called as a meta-GGA. And there are two classes over here. One is where they now have added an additional dependence on the Laplacian of the density, and which is what people call as either orbital-free exchange correlation functionals, because you don't have any orbitals, it's still dependent on the electron density, or some other people call Laplacian level exchange correlation functionals. And some other meta-GGAs such as SCAN, what they use this parameter tau, which is the kinetic energy density. So we can evaluate the kinetic energy density by taking the gradients of the Kohn-Sham orbitals, take the absolute value, square it, and then sum over it. That gives you the kinetic energy density at a given local point. And then that's also part of the exchange correlation function. And this goes back to the point that Volker was mentioning yesterday, that when we did this split, there is the Hohenberg-Kohn functional we know explicitly depends on the electron density. The TS we know depends on electron density, but it's an implicit dependence because it does come from the solutions of your Kohn-Sham orbitals. So one of the thinking was that, well, because this depends on size, maybe this also can depend on the size. So, and that is kind of some of the thinking of putting in this kinetic energy density into the functional approximation. And also there has been a formal extension of the Kohn-Sham formulation called the generalized Kohn-Sham formulation, which shows some of the same statements, that the Hohenberg-Kohn theorem, shows. So it is at least the reason why the reason why things will still be right if you were incorporating the single electron Kohn-Sham orbitals is actually grounded in proper theory at this point. Now the next rung of the ladder is so even at this particular point, one of the serious issues with all of these functionals is the self-interaction error. Because we go into describing all these many-body interactions just solely using electron density, once you go to an electron density, if you have a single electron system, you still have an exchange correlation potential and functional for that. But ideally for a single electron system, there are no interactions with another electron. So the electron is interacting with itself, right? And that is the self-interaction error, which is present in pretty much all these functionals that depend solely on rho. That self-interaction error is not there in the Hartree-Fock formalism because yesterday when I introduced the Coulomb integrals and the exchange integrals, the Coulomb integral and the exchange integrals exactly cancel each other when I and j are the same, right? So that is some of the things which motivated people to look at functionals where you also put in part of the exchange. And initially in the 1990s, people actually tried to put in the full exchange and then put in just a correlation which depends on the density and see how the energetics are. And that came out to be very poor. So once you put in the exact exchange, even the correlations cannot be treated at a local level. The correlations also become non-local. But a happy compromise was then the community figured out that you don't have to use the full exact exchange. You can use only a fraction of the full exact exchange, which essentially cancels out some of the effects that are coming from the non-local aspects of the correlations. And that has especially done a reasonable job in terms of improving the accuracy of DFT calculations for certain properties such as band gaps, which was very important when the semiconductor industry was trying to use these calculations to develop new materials. And more recently, there are more accurate theories which are based on random phase approximations and other aspects which are being developed. So essentially, if we look at it, the accuracy that we want to get to is that chemical accuracy, which is, can we get to that 1 kilocalorie per mole, which translate to an error in terms of energies to be 1 to 2 millihartry errors. So that is the error that is acceptable from if you were thinking about chemical accuracy. And I think many of these particular functionals are still very far away from that particular chemical accuracy. So there is an increasing push to kind of make these things more and more accurate. Okay. So with that, I'll just, it's easy to imagine what these functions look like. They just depend on the density, gradient density, or depends on the Laplacian of the density. But when it comes to the exchange operator, so I defined the exchange operator yesterday. So this is how the integral looks like. It's a double integral, right? It depends on positions of 2 electrons at a time. And one of the challenges is that okay, there is a sum over I and j. So it can be fairly expensive to kind of evaluate this. And as I mentioned, the class of functionals that people have developed and then are widely used, they don't use the full exchange, but they use only a fraction of the exchange. And the correlation is treated at some level of either an LDA or a PBE type approximation. So here, for the PBE0, it's 1/4 of the exact Hartree-Fock exchange, 3/4 of the exchange of the PBE, which is a GGA approximation, and the full correlation of PBE. And then there are other popular family of functionals called HSE, M06, and other things. So these things are either names of the authors, who have developed these functionals, and in the M0N family, these are the Minnesota functionals, where a lot of functional development has happened over the years. Okay, so still, I mean, even despite all this progress has been to date, if we look at the fundamental gaps, and which is one of the important quantities that people want to compute, there are other electronic structure approaches of computing the gaps. But if we can do it at a DFT level, then it's useful because it's computationally more efficient. So even if you look at the fundamental gaps for these hybrid functionals, which include a part of the exact exchange, the errors are still large. You want these errors to be somewhere of the order of 10 MeV or so, but these errors are more of the order of a few hundreds of MeV. So an order of magnitude higher than what we ideally would like at this point. Okay, and when it comes to hybrid functionals, as I mentioned, it can be computationally expensive. because you have an index over like I and j, and that means that like you have to compute when you're computing the action of the exchange operator on any trial vector, it involves computation of a extended integral over here. Now, there is some interesting aspect that this particular kernel over here, the 1 over R kernel, is a Green's function of the Laplace operator. So which means that if you were using a plane wave code, this is not too hard to compute because, well, you compute the Fourier transform of this particular product, multiply by k square, and then take the inverse Fourier transform, right? So that is one of the reasons like why plane wave codes work well and efficiently for hybrid calculations, and also are able to take some advantage of the existing power on the GPUs because they're able to like parallelize this piece of the calculation much more efficiently than the other pieces of the calculation. So in the real space world, there are other ideas like that have developed. I mean, if you do this calculation naively, like that can have a higher cost than cubic scaling of density functional theory. So people have developed ideas such as adaptive compressive exchange operator, and the main idea is that as you are computing, okay, I didn't write down the generalized Kohn-Sham equations over here, but as you are taking this exchange operator in your Kohn-Sham orbitals, you can keep this exchange operator fixed and then iterate over your trial wave functions and then have another outer loop for the convergence of the exchange operator itself, right? So that is the main idea behind the adaptive compressive exchange operator. And then also the quantum chemistry community has tackled this particular issue by exploiting ideas of resolution of identity, where instead of they cut down on the number of basis functions, where instead of working with the basis functions native to what are used in describing that solution vector, you compute this product and then solve it in another auxiliary basis. And also, when you go to other quantum chemistry codes, the 1 over R kernel can be well approximated using a linear combination of Gaussians, and that allows you to compute this 2-electron integral in a much more natural manner. So that's actually one of the strengths of the quantum chemistry codes over the more systematically convergent either plane wave basis or other real space basis discretization, such as finite difference, finite elements, or wavelets. So, Volker, did you have anything to add on this?
You know the old discussion about resolution of identity, right? So that's one thing worth mentioning is probably that this has been kind of always done in these calculations. So it goes back to
yes, it's an old idea, right? I mean, it's
was in Charit, I think, in 1957.
Yeah.
This is the technical report for the paper that they published in 1951. So anyway, so they've always been.
Yeah.
This idea has always been.
Yeah. So these ideas have essentially come about like when people have been thinking about this. In fact, the many-body quantum problem itself, when you have this 2-electron integral kind of sitting there, and then these and that's, I believe, like where the ideas originated from as to like how do you improve the efficiency of like evaluating this kind of 2-electron integrals. So yeah. So this is kind of like this is more recent work of Head Gordon. Like there are many other ideas in that paper, but I was just trying to say more broadly what the idea was here.
I have a naive question. So for the integral for R prime, so is that defined for the whole R3 space?
So if it was a non-periodic problem, yes, that would be defined on the whole R3 space. But you don't necessarily need to like compute it on the whole R3 space, especially if you're thinking of this as a potential, because you only need this potential in the region of the compact support of this function.
So that is damping very fast if far away, right?
This falls off exponentially.
Exponentially?
Yeah. So this Kohn-Sham, the orbitals fall off exponentially. So you can take advantage of like that aspect as well, where you can compute this particular potential very accurately up to a particular point, and then like even if it has some error in the far field, that's not going to affect your calculation.
Do you have some specific example for the phi x, probably you call psi j or psi r? Do you have some particular function form?
So typically these things look like, I mean, they're not exactly that, but they look like your SPDF orbitals, right? So you can take an atom, see how the SPDF orbitals look like, and then these have that kind of a flavor in the non-periodic setting, right? If you're in a periodic setting, then you have to bring into account just like I mentioned the block flow K theorem, and then be careful about how you handle these exchange integrals in the periodic setting.
So that is, you basically don't have any explicit form for this kind of psi j?
No, so this is coming as part of the calculation itself, right? So these are the Kohn-Sham orbitals where these are the eigenfunctions that you're trying to compute. Yeah. Okay. So the other approximation that comes in density functional theory is a pseudopotential approximation. And the main idea behind the pseudopotential approximation is that, well, the core electrons are very tightly bound to the nucleus, and these are not going to participate mostly in the binding. And if you're interested in understanding the binding aspects or any other properties that are much more tied to the binding of atoms, well, it's only important for us to capture the nature of the wave function outside a particular core, right? And also, it's the valence electrons which probably control many of the electronic structure properties. So maybe we can solve only for the valence electrons, right? So that was the strategy. So what people did was that they started constructing fictitious potentials. Now, you no longer have the external potential, which is a Coulomb potential. Having a Coulomb potential will become very challenging because you will start seeing rapid oscillations in the wave functions as you get close to the nucleus. So they did not want to kind of capture all those oscillations because maybe that's not important. So they constructed a fictitious potential called as V pseudo, which outside a particular region actually has the right 1 over R decay, and also which produces the same behavior of the wave function outside of this RC or this particular core radius, right? Because the belief is that it is in this region that the binding between the atoms happen. That is where the valence electrons properties matter to the electronic structure and subsequent properties of materials. So some of the benefits of the pseudopotential approximations are that it improves the regularity of the solutions because now you have smoother pseudo wave functions. So you don't need to resolve all these rapid oscillations near the nucleus. It also reduces the number of eigenstates that you need to solve for. So if, for instance, you take magnesium has 12 electrons. If you construct a pseudopotential, in the valence orbital, it has only 2 electrons. So you're cutting down the number of electrons that you're solving by 5-fold. And if you think that the scaling of the density functional theory calculation is itself cubic scaling, that's tremendous advantage. You're now talking about 100-fold speed ups, just by going to the pseudopotential approximation, just from the perspective of solving for lesser number of electrons. And a further added advantage will be because you don't need as much refined basis sets as that of an all-electron calculation. So 2 aspects. While pseudopotential calculations are probably the most widely used these days, but there are some very important limitations, right? So in some cases, I list out over here, they may not be as good, when you are in very high pressure regimes because you're compressing the atoms to come really close to each other, and then the cores can start deforming, and then whatever assumptions that you made, to have your pseudopotentials for more conventional material systems can break down over there. And there have been works coming out of Matthias Scheffler's group and other people, other groups as well, where they've shown that pseudopotential approximations may not give you the right, there can be errors in the magnetic properties, appreciable errors. There can be appreciable errors in spectroscopic properties. So if you were computing spin Hamiltonian parameters, we also have done some work which showed that the all-electron description and then the pseudopotential description actually give you different spin Hamiltonian parameters, appreciable to the fact that, like, that it's important to resolve that discrepancy. And some of the widely used pseudopotential methods out there are norm-conserving pseudopotentials, the Trillier-Martins, and the more recently developed optimized norm-conserving Vanderbilt pseudopotentials. Some of the other widely used ones are the ultra-soft pseudopotentials by Vanderbilt and the PAW method by Blockl. Okay. So now I want to switch gears and start talking about numerical discretization methods. And you pick your favorite DFT code, it has a discretization method, right? So and in the first one I'm going to discuss is going to be plane waves, because that is the most popular workhorse of electronic structure calculations. So in fact, if you look at the fraction of the computational resources that are occupied on workhorse supercomputing machines like those at NERSC, like Perlmutter or something, almost 25% of the compute cycles are occupied by electronic structure calculations, and most of it being DFT calculations. And if you look at among DFT calculations itself, probably VASP has a majority share, of these calculations. And if you add the other plane wave codes such as quantum espresso and other things, that becomes a significant fraction of the cycles that these codes actually occupy. So if you look at plane wave discretizations, and under the pseudopotential approximation, of course, you have VASP, you have quantum espresso, Abinet, QBox. QBox is actually one of the more scalable plane wave codes out there, at least on CPUs. I've not seen much on GPUs. And in fact, some of the ideas that Eric was talking yesterday were are part of the QBox framework. And CASTEP and GPAW has multiple basis sets that are available. You can either do it using finite difference discretization, plane waves, or they also have an atomic orbital discretization as well. So as I mentioned, plane waves are very attractive because firstly, they provide systematic convergence, right? So you give an accuracy level, you can go on turning up your plane wave basis to kind of hit that particular accuracy level. So systematic convergence is one of its strengths. And then the second thing is, when it comes to periodic systems, and thus solid state physics calculations, for periodic systems, arguably, plane wave basis is also the most efficient basis set, because you can get to that particular accuracy in lesser number of basis functions compared to any other systematically convergent basis set, such as finite, and here I'm thinking finite difference, finite elements, or wavelets, right? And the other advantage is its efficient computation of the Coulomb kernel in the Fourier space. So if you have to evaluate either your Hartree potential, or you have an exchange operator where you have the Coulomb kernel and you have to evaluate that is done very, very efficiently in Fourier space, right? But some of the disadvantages are that it's limited to pseudopotential calculations. It lacks spatial adaptivity. That is, if you think about a plane wave basis, it has the same spatial resolution everywhere in the domain, no matter whether there is a particular atom there or not, right? So it cannot handle spatial adaptivity. And there also have been some very recent efforts to extending the plane wave calculations, and I believe this was an implementation in QBox, to even all electron calculations. That's a very recent paper, just I think a couple of weeks ago, appeared in JCTC. So the other downside is that it's limited to periodic boundary conditions. So if you have, for instance, an external field which cannot be described by a periodic boundary condition, then you either have to take a very large vacuum, which is going to drop the efficiency of the calculation very much, or you just don't use that particular basis set, right? So, and in terms of scalability, so I think this is becoming the Achilles heel for some of the plane wave codes, that So plane waves like scale very well. I mean, of course, you can do k-point parallelism, you can do band parallelism, that is, you can compute the different bands on different processes. But one thing which FFTs cannot, or plane wave codes have not been able to do like really well, is the scalability of the Fourier transforms itself. Now, this naturally puts a lid on the access of system sizes, because think about you want to do 1,000 atom calculation with 10,000 electrons out there. There is a ceiling on how low, or rather there's a floor on like, how low are the number of nodes that you can fit that particular calculation on, because you have a plane wave cutoff, you have so many wave functions, so you have to throw this on a minimum set of nodes. So which means that you are bound to like, parallelize your FFT grid. And if that point like, starts exceeding the point like where FFTs actually scale well, then you're pretty much like, going to be bound by communication for all the plane wave codes. And that is the reason, like you may see that the scaling falls off once you start going to like larger number of nodes in the plane wave codes. This happens in CPUs a bit more later in terms of the number of nodes, but it happens in GPUs much, much faster, because you've exhausted all your compute. On GPUs, like the compute is really, really fast. You've exhausted all the computes, and that fallover point, like, where you become communication bound, happens much earlier on a hybrid architecture than like, just a multi-core CPU architecture. So the next category that I want to discuss are the atomic orbitals basis set. And Volker, like, since you work with these basis sets, like, feel free to add any comments, like, on this. And I think we're also going to hear in the first week of the workshop, Volker is going to present about FHI aims and all the capabilities in that code and how they're scaling it up. So this is a basis set that is much more popular in quantum chemistry codes. And the atomic orbital basis sets are either like Slater basis functions, these are or Gaussian basis functions, or numerical atomic orbitals. So the Slater basis functions is used in Amsterdam density functional code. The Gaussian basis functions are popular in Gaussian, NWChem, QChem, CP2K, CSTA, and so on. And these numerical atomic orbitals are what are the workhorse, like, or the driving engine of FHI aims. So one of the key advantages is that these are reduced order basis functions, which are tailored for a particular atom. And in the case of FHI aims, they just don't use like just single atoms, but they also use some small molecules to kind of tailor this so that it captures the condensed matter system in a more effective manner. But you typically can get away with order tens of basis functions per atom, like, for these atomic orbital type basis functions. And also the other advantage is that this is a common basis that can be used for both DFT calculations as well as wave function based calculations. Because unlike DFT, when you're going to wave function type theories, you cannot afford to have the basis set disadvantage that even plane waves and other systematically convergent basis sets are. Because even in plane waves, even if you're doing a pseudopotential calculation, you're talking about still a few hundred basis functions per atom. And with those number of basis functions per atom, you can never imagine doing a more higher level quantum chemistry type calculation. So you really need low number of basis functions in those regimes. It can be used in both all electron and pseudopotential calculations. And there is this efficient way of dealing with the Coulomb kernels using a combination of this resolution of identity idea, as well as expanding the 1/r kernel in terms of a linear combination of Gaussian functions. And once you do that, like, what happens is you can then write your integrals in a nice manner and then, like, efficiently compute those Coulomb integrals. So the disadvantages, however, are that if we give an arbitrary accuracy and then we say, okay, we want to converge to this level of accuracy, the atomic orbitals may not be able to. They may be able to for some systems, but they may not be able to for some systems. And the systems where they especially face, like, some challenges are in metallic systems, like, where you can have kind of longish tails. And once you start dialing the basis set up, you can also run into some kind of linear dependency issues. And that is one of the limitations of this. But I think, FHI Ames is trying to, address those limitations. But Volker had a comment or a question.
Comment on two things, right? So the metallic systems are actually not a problem. That's a very common. Not you didn't say this, but other people have. Have confused the Bloch phase with the plane wave, right? And so this.
Oh no, yeah.
And I think for DFT, systematic convergence to something like milli-vector volts per atom and total energy is feasible. So that may depend on the basis functions. Gaussians may be less well shaped than NAOs, but eventually for DFT you can do this. Actually, if you want to go to response, so to a generalized, systematically converged expression of response function for the many electron case, which basically includes all the wave function-based methods.
Yeah.
The plane wave methods are actually more systematic because they can go without the basis. But there the problem is a different one. So I think the problem in the many electron case is actually almost infinite. Right? There the local methods all struggle with the few basis function methods all struggle with the fact that they need a larger Hilbert space to capture electrons.
Yes.
So actually, I think the biggest GW calculations that I'm aware of are working GW. You can argue about details like what is the plasma pole model they used or not.
Yeah.
Somebody in the audience may actually know this. But I think the biggest published calculations is plane wave.
Yeah, it's by the West Code, right? Yeah. For the GW calculations, yes. But I was also having for instance, things like CI calculations in mind, where you have to construct these Slater orbitals, and it becomes very, very challenging. When you have a large basis set, I mean, you basically get maxed out. If you're trying to go beyond 30 basis functions or 40 basis functions per atom, becomes very challenging for those quantum chemistry types of calculations, I believe. Yes. Yeah, the questions, comments? Okay, so the next thing I want to talk about is something which is in between these atomic orbitals and plane waves. And there was this natural need for doing periodic calculations, but also at all electron accuracy. And this comes about when you are dealing with extreme pressures that you want to study the equation of state, you want to understand the electronic structure, as well as you have a solid state system where the properties that you're interested in actually are also significantly influenced by the core states. In that case, you will have to go towards an all-electron type calculation. And also, you have to apply periodic boundary conditions. So what's some of the basis sets which enable you to do that? Are this class of APW, LAPW, or LAPW plus LO type basis sets. And the main idea is that, well, let's say that you have a transition metal, you have oxygen, you have hydrogen sitting there, and then this is your unit cell. What they do is they create these spheres called as muffin tins. And inside this particular muffin tin, what they have is they write your basic variable of interest now, which will be the Kohn-Sham functions, or essentially the functions, the equivalent of the Kohn-Sham functions that are periodic on the unit cell. Inside the muffin tin, you write them as an expansion of certain atomic orbitals. So these are essentially radial functions multiplied by spherical harmonics. So that's the structure inside the muffin tin. And outside of this, you have plane waves. And then they have to do some boundary matching to make sure that the eventual function is going to be C1 continuous across the boundary. And ensuring that particular C1 continuity can bring about some restrictions on the K-point grid that you choose, And there's an energy parameter over here which comes into play when you're doing this matching boundary conditions, and then you might have to pick like, the right energy parameter. So you don't have as much flexibility in this basis as you would want to, but it essentially serves the purpose of trying to capture those fast oscillations on your wave functions right near the nucleus, but also provide the plane wave, like periodic boundary conditions in the interstitial regime. So the advantages being that like now you can do periodic all-electron calculations. It has some level of tunable accuracy, but the disadvantages are that it suffers the same limitations as the plane wave basis sets. And to the best of my knowledge, I think there are not many codes like in the LAPW suite of like codes like where they scale very well on multi-node architectures. So the scalability happens primarily on the k-point parallelism, but to the best of my knowledge, correct me if I'm wrong, Volker, not very much on the domain decomposition aspects of things. So yeah, as I mentioned, like scalability, coming up with proper implementations that are parallel scalable can be difficult. Okay, so then the next class that I want to like briefly touch upon are real space methods, either the finite difference, finite elements, or wavelets. So some codes which are based on finite difference are Parsec. Octopus is a TD-DFT code, but I believe like you can also do ground state calculations, and Spark and Rescue, which are more recent entrants. And in terms of codes based on wavelets, it's Big DFT, which has been around for some time. And codes based on finite elements, this is again like a recently developed one, which we work on in our group, which is DFT-FE. So some of the advantages of these real space basis sets are all of these are systematically convergent. The discrete Hamiltonian, that is, once you discretize your Hamiltonian, the Hamiltonians are sparse. So now you can start taking advantage of sparse linear algebra tricks to probably get more efficiency or better scalability and things like that. So these have been shown to be parallels, demonstrate good parallel scalability. And also like large scale systems of the order of like 100,000 electrons and beyond have been demonstrated recently. These are amenable to GPU porting as well. But the main disadvantage for all these more systematically convergent real space codes is that they have a larger footprint, memory footprint, than the plane wave codes. So typically, for pseudopotential calculations, if you're comparing against, let's say, an ONCV calculation, the finite difference as well as the finite elements take somewhere about like 5 times more degrees of freedom than the plane waves. So if you have a small machine and you're trying to like fit your calculation into a small machine, these codes would not be suitable. That's where like the plane wave codes are the best, and then they are the most efficient. And in terms of one other advantage of finite elements, which for instance finite difference, like at least in the present implementations doesn't have, is the spatial adaptivity. So you can systematically refine regions of interest and coarse grain regions of interest, so that allows you to like handle both pseudopotential and all electron calculations. Although in DFT-FE there is an all electron implementation, but then it's not relative. It doesn't account for relativistic interactions or relativistic effects. And one of the aspects that like we are trying to do is also enrich this finite elements with atomic orbitals. And now that will be like an enrichment space without sacrificing the systematic convergence of the finite elements. So we expect that can substantially bridge this particular memory footprint disadvantage with regards to plane waves. We'll never be able to like get as low as the atomic orbital spaces, but I think that like with this enrichment you can get substantially lower memory footprint than the plane wave basis itself. So, okay, so now when it comes, yeah.
So with the enrichment, I think that many years ago Trump asked this, right?
Yeah.
My understanding was that in that case, though, they ran into issues with badly conditioned basis sets that were hard to resolve somehow.
Yeah, so the thing is, so they followed a slightly different type of enrichment, which is the partitions of unity finite elements, where what they do is they take their enrichment function and then also multiply that with the finite element basis functions. And the works that I'm aware of were just demonstrating that you will drop the number of basis functions that you will need to get to a particular level of accuracy by a substantial degree. But they never took it to the point of really taking it to large scale calculations, testing the scalability and other things. Because there are certain other aspects that come into play, like when you're looking at these partitions of unity finite elements, that you can run into linear dependency issues also in that particular case. And you have a more sparser grid because you're multiplying by the finite element basis set, but that linear dependency becomes a substantial bottleneck. And it is not an orthonormal basis. And then the inversion of this becomes a substantial bottleneck. So all these issues have essentially either for that reason or other reasons that they moved away. There's some work still that's going on, like John Pask and Sukumar still do work in that particular direction. There are also other people who have been exploring this. But what we do differently is that we don't use the partitions of unity. We take the finite element space and just explicitly enrich them with atomic orbitals. But these orbitals are then orthonormal or orthogonalized with respect to the finite element basis, so that you take out the space, you take out that linear dependency issue then between the enrichment functions and your finite element basis functions. So we have been able to, so this is not yet in the DFT FE code, but in the in-house code, we have been able to demonstrate using this enriched finite elements in the non-relativistic setting, all electron calculations up to 10,000 electrons. And we do get a substantial benefit in terms of, we get a 100x boost in terms of computational efficiency. And also in many cases, we are able to outperform LAPW and APW codes, LAPW plus LO codes. And this also has been demonstrated both for non-periodic and periodic systems. So, and also we have demonstrated forces and stresses. So all the pieces are there, just that we now need to kind of revamp the DFT FE code to put in enrichments, which means that we have to touch the base layer of the basis, so which means complete rewrite of the code. So, yeah. Okay, so now I just want to go back to some aspects about the solution of the eigenvalue problem itself. So as I was emphasizing, there are two key aspects. One is the solution to this eigenvalue problem, which scales cubically with the system size. We have to compute as many eigenstates as there are the number of electrons in the system. Sometimes the evaluation of this effective potential, so the way I'm writing over here is that this is a local effective potential just dependent on the electron density. But once you have exact exchange, the evaluation of that V effective and action of the exact exchange on these trial vectors can become the dominant cost in many cases. Now, when it comes to the solution of this eigenvalue problem, depending on the choice of the basis, many options open up. And this is where every code and every group of developers of DFT have to make a choice. So depending on the basis set, you can either end up with a standard or a generalized eigenvalue problem. In many cases, even if you have a generalized eigenvalue problem, like you will in the case of atomic orbitals, they compute the inverse of the overlap matrix and then transform it into a standard eigenvalue problem, because you have more methods that are available for standard eigenvalue problems. Also, the algorithms that one may want to use and may want to develop will depend on whether this discrete Hamiltonian is dense or would it be sparse. And in the case of plane waves, they do not even want to work with constructing the discrete Hamiltonian, because it's going to be fully dense, and then evaluating those matrix elements will be very, very expensive. So they just rely on a matrix-free approach, where what they implement is the action of the operator on a vector, right? And that involves Fourier transforms. So And then the other challenge is also once you start getting to the exascale computing architectures, and one of the reasons why DFT codes may want to go there is because it would open up access to larger scale DFT calculations. But once we go to larger scale DFT calculations, besides all these considerations, worrying about parallel scalability, better algorithms, one of the other important aspects to worry about is the convergence of the self-consistent field iteration itself. Because once you start getting to larger and larger systems, the conditioning of this map becomes worse and worse. And if you don't have good preconditioners or mixing schemes to get this particular problem under control, then that also can put a limit on what is the largest system that one can study. So in terms of the numerical solution to the eigenvalue problem itself, one of the approaches is just do a direct minimization, right? Instead of looking at it as an eigenvalue problem, you can look at it as a variational problem where you're minimizing over all the wave functions, and that would be a nonlinear minimization problem. That is a fine approach, but it soon starts to run out of steam once you start getting to larger and larger calculations, because you have to rely on quasi-Newton based nonlinear solvers, and you can get stuck in a local minimum, you might not converge, and all these issues show up with a direct minimization. So SCF doing the self-consistent field iteration by solving an eigenvalue problem is still considered the go-to approach for solving the DFT problem. So now if we look at the iterative approaches to solving the eigenvalue problem, these are some of the more widely used approaches. So in any of these cases, especially when you're going to many core architectures, and especially on GPUs, you do want to use the blocked versions of these problems because you're interested in computing many eigenstates at the lower end of the spectrum. It's better not to do one eigenstate at a time, but rather try to take advantage of the increased flops that you can get by trying to compute the L number of eigenstates in one go. So and the blocked preconditioned block Davidson method, the RMMDIS, which is in VASP, and this is what Quantum Espresso uses. The preconditioned locally optimized block conjugate gradient method. So these are all the various approaches that have been implemented in many of the workhorse electronic structure codes. But one of the approach that is actually picking up some interest and popularity is this Chebyshev filtered subspace iteration. This was proposed by Yusuf Saad and Jim Chelikowiski and co-workers in 2006 in an implementation, in a finite difference implementation in the parsec code, and we have adapted this into the finite element basis as well, and we see tremendous performance of this particular eigensolver. And this is what I'll quickly mention what the main idea behind this is. So especially when you're interested in very large scale problems, what the Chebyshev acceleration technique does is that, well, we're interested in solving this eigenvalue problem, and the eigenstates that we're interested in are at the lower end of the spectrum. So let's call these eigenstates as the wanted spectrum, and let's call the states that we don't care about as the unwanted spectrum. And the main idea here is to, once you have information about the lowest end of the spectrum, the highest end of the spectrum, and a reasonable guess for where that particular chemical potential is, right? You can scale and shift this Hamiltonian such that the unwanted spectrum comes between -1 to 1, and the wanted spectrum comes to the left of -1. And the idea behind Chebyshev filtering is that you can construct a Chebyshev polynomial filter of the scaled and shifted Hamiltonian. And one of the properties of Chebyshev polynomials is that it is bounded between -1 to 1, but grows rapidly outside of -1 and 1. So now our spectrum in the scaled and shifted Hamiltonian is such that the unwanted spectrum is coming between -1 to 1, and the wanted spectrum is right to the left of -1. So now once we start hitting this Chebyshev polynomial filter on a bunch of random vectors, what it does is it kills all the components in these trial vectors along the unwanted spectrum and starts magnifying the components along the wanted spectrum. So what eventually you end up with is a filtered space, which is very rich in the wanted spectrum of interest. And so hence, you can now project your original problem into this filtered space and then solve a much more smaller eigenvalue problem in terms of the dimensions of the Hamiltonian matrix itself. So that's the basic idea. And one of the other advantages of this Chebyshev filtering is that this can be written as a recursive iteration, which only involves a matrix multiplication, a h times x. So you have then much of the work that you're doing, which is concentrated in that particular kernel, which can be well optimized and also potentially get a good amount of performance on GPUs as well as get good scalability. So as I mentioned, like you start with an input electron guess, you construct your discrete Hamiltonian, then you get your Chebyshev filtered subspace, and this Chebyshev filtered subspace, after you do the filtering, is not. It's going to be poorly conditioned because like all the vectors start kind of aligning towards the eigenstate, which is the lowest eigenstate. So you have to do an orthonormalization procedure over here to recover a good conditioning of the basis. Then you project the problem into this basis, and then you diagonalize this much smaller Hamiltonian. And once you diagonalize it, you can get back your original vectors in the space, compute the electron density, and then do the self-consistent field iteration. So I'm running out of time. So, and the other aspect that I mentioned is the solution of the self-consistent field iteration itself. It is a fixed point iteration, which is a map, and F is the map which actually involves the solution of the eigenvalue problem itself. So you can think about from just a mathematical standpoint that you can construct this kind of a quasi-Newton type update, but you don't have access to this Jacobian information explicitly because you don't have information of this map F explicitly. So people have to do some approximations to this Jacobian, and that is at the heart of many of the methods that have been proposed, like Anderson, Broyden, Kirker, elliptic preconditioners. And there is also a nice article which actually discusses this fixed point iteration from this perspective and then talks about the pros and cons of these various methods. So I encourage you to take a look at it. So the final thing, I might not have much time because I'm already, Virginia gave me a heads up, is that there are also, I mentioned that conventionally the density functional theory calculations are cubic scaling. But there are regimes where you can actually reduce the computational complexity to be lesser than cubic scaling. So these are what are called as linear scaling approaches or reduced order scaling approaches. And the main idea behind this is that the eventual quantity of interest that we are after is the electron density. We really don't care about the Kohn-Sham eigenfunctions. The Kohn-Sham eigenfunctions are a means to get to this electron density, right? So now think about a case where you have a system with a band gap, where these orbital occupancy factors are going to be 1. Then you don't have to actually go and compute the canonical eigenfunctions, which require a diagonalization of the Hamiltonian, but you only need to compute the space that spans those eigenfunctions. And once you have the space that spans eigenfunctions, you can compute your density from there. Right? So that's the basic idea, behind these reduced order scaling approaches. And many of these reduced order scaling approaches are recast into the solution of what is called as the density matrix. The density matrix is nothing but you consider the Fermi-Dirac function of the Hamiltonian matrix minus mu I, and there are techniques where you have expansions for this Fermi-Dirac function, and then the number of expansion terms that you have to take will be proportional to the spectral width of the Hamiltonian itself. And so there's a nice review article by Stefan Godecker, which discusses this as well as many other reduced order scaling techniques. And there's also another article that I'm going to point out, a more recent one. But in any of these particular techniques, to get the true linear scaling, you will really need that this gamma, the density matrix, eventually remains sparse or diagonally dominant. But typically what happens is once you start doing this Fermi orbital expansion, the bandwidth of the matrix starts to grow, and then you lose out, and eventually you don't recover a linear scaling technique. Or if you want to recover a linear scaling technique, you need to introduce a truncation. That is, you throw out all the elements in your matrix below a particular value, and that can create numerical errors, and then you have to worry about how accurate the calculation is and things like that. And the conquest code is also based on this density matrix idea, where they construct locally compact functions, and then construct the density matrix to be this, and then optimize over these coefficients ki alpha, which is essentially the representation of this density matrix in this particular basis. And as I mentioned, if you are able to compute just the space that is spanning the eigenstates of interest, and you have a system with a gap, then you don't need your canonical eigenfunctions, and that's some of the ideas that were exploited in the works of Carlos Garcia Cervera and co-workers. And we have ourselves worked on extending this idea to also systems which don't have a band gap. And these are two very good articles people can read about in terms of linear scaling techniques. And as I mentioned, these have to be used with some caution. These rely on some kind of truncation or assumption of locality or compactness of the density matrix, which always may not be the case. It depends on the material system that you're looking at. So implications to Exascale, there are three aspects I think people, from my perspective, that people need to think about. One is the basis set scalability. There will be sometimes inherent limitations based on the choice of the basis set as to how much extent of data transfer you need to do, and how much amount of and data transfer can be access costs or communication costs, right? And what is the ratio of the data transfer to really the compute that is happening, and that puts a ceiling on how much scalability that you can get for these codes. And also there could be linear dependency issues in terms of how some of the basis sets are implemented. So once you start going to larger scale systems, this needs to be also looked at carefully. And in terms of algorithms, definitely blocked approaches are better because it gives you a higher flops, higher throughput performance. If you're able to recast the algorithm such that you have efficient matrix products, then that can get good parallel scalability on GPUs. If the codes can use mixed precision algorithms and ideas where you're hiding compute behind communication, that can also improve the performance and scalability on these hybrid computing architectures. And as I mentioned, asynchronous compute communication is another useful aspect. And in terms of software stack, it'll be great if the generic linear algebra libraries really take off and then allow the capabilities to do these operations in a multi-node setting. That will just be a game changer for, I think, many DFT codes. The other key aspect, that developers, and some of them are in this room, have to grapple with is there is a new programming paradigm, that comes up, every few years. So the code management becomes a nightmare. So we worked a lot, to port our code to CUDA, and then all of a sudden, we don't have a big enough CUDA machine. The next biggest machine is based on HIP. And then maybe the next one is due to be, the next biggest one is going to be on using SYCL, right? So it is a challenge that the developer groups are grappling with as to how to maintain these codes. And then also, as Eric was pointing yesterday, if many DFT codes are Fortran based. So what does it mean in terms of the support going forward for the compilers? The compilers will be there, but are they going to give you the best efficiency that you can get from that particular machine? And these codes have been, some of these codes, legacy codes, have been had many hundreds of man years of effort that has gone into building this code. So in some cases it may be easy to make this adaptation, and in some cases it may not be, right? So these are all, I think, the challenges that the community is facing in the Exascale era. And with that, I want to point to this particular reference or an article on archive. So this was a roadmap article this was a community effort. Like, some of the co-authors are in this audience, like including Danny, Volker, some of the participants in the workshop, one Julia Gali, David Bowler, are also co-authors of this article. So what this article is doing is to try to survey the lay of the land in DFT codes and how well they're positioned, like, or what their plans are for the exascale era. So it's going to, like, discuss, so it covers about 14 codes, all these codes, like, over here. These are short, like, descriptions of each of the codes, 3 to 4 pages at most. So it tells what the current state of the art is, what the niche of that particular code is in the whole electronic structure community, what the development and implementation plans are over the next 5 to 10 years, and how each code is transitioning towards the exascale computing era. So I think for those people who are trying to get into DFT calculations or trying to look for codes, like, which will meet their needs, I think this can provide a good glimpse of where things are at this point. And then, like, they can contact the respective authors of each of the codes, like, for further information. So,
you mentioned that FAST was one of the most popular. It seems striking.
Yeah. So this was an effort like that. Danny and I were, like, coordinating to kind of get this roadmap article together. We invited VASP to contribute. They didn't want to. So so some of the codes, like, whom we invited and did not contribute were VASP and ADF. I don't know if, like, any aspect of the commercial aspect, like, plays into the role in being part of, like, such an effort. But yeah, it's not meant to be an exclusion from our end. Yeah. Okay. So I guess that's all I have, and thank you for your attention, and sorry for getting